everybody. There's 36 people on the call so far, which is, you know, a lovely group. And I expect quite a few more will be joining us because there's quite a few more that actually are registered. And a few that are registering even now as we speak. And I'm Melanie Mindlin. I know a lot of you. I'm in Ashland, Oregon, the unceded territory of several native tribes, including the Klamath, the Shasta, the Decapitidi, and the Degelma, as well as others. Just want to acknowledge them and thank them. Yeah, so I am a partner in Siskiyou Permaculture, who is one of the sponsors of this event. Siskiyou Permaculture provided their extensive mailing list and their website for the registration process. Thank you very much. And also my hat. We're also partnered with my other hat, which is coordinator of the Fire Ecology Restoration Project, which all of you on the Siskiyou Permaculture mailing list, which is a lot of you, have been hearing a little bit about our project, which is associated with the Permaculture Institute of North America. We're very excited to be starting this opportunity to train people, do research, and generally move forward the field of doing restorative forestry centered around biochar. And any of you, especially you younger people who are just launching your career, I strongly encourage you to consider restoration forestry, and you know, to get in touch with us to see a way forward. And so this talk this evening is also originally sponsored by and provided by our association with the Firefighters United for Safety, Ethics, and Ecology, FUSE. And we want to thank them for sponsoring us and helping us out here. And we did a really exciting project with them that started this spring with a in-person biochar workshop at Hot Lum Eco Regeneration Camp in California that Ken did with us. And now we're doing this, and we're going to cap that whole project off with an exciting video production by Mitchell Davidowitz. And Mitchell, if you're on, thank you very much. We love your work. So let's see, I guess one other thing I wanted to say before we move forward is just Siskiyou Permaculture sponsorship. We're doing a number of other events. There's another talk 1 week from now, next Wednesday. Hazel will be talking about 10 steps to localization, becoming a people of place. And I encourage you to join us for that. It's got a similar registration, free to whatever. We appreciate your donations, but nobody is turned away. And Hazel will be giving another talk on December 4th, a storytelling whose topic has yet to be announced. And then we are offering in February, inshallah, we will be giving our famous in-person social forestry course, which is already half full. So if you're really keen to come and do it with us, register soon. We still have a couple of work trade positions available with that. And then with any luck, we will be giving the permaculture design course next winter, spring as well. So with all of that, I am now, let's see, oh, one other thing, Zoom stuff. So please keep yourself muted during the presentation and don't unmute yourself unless I invite you to do so. If you want to say something, please use the tools at the bottom. There's one that's on your bottom toolbar that says reactions, and that will give you a bunch of emoticons. And that is where we raise our hands, right? Or am I getting this wrong? Karen, help me out here. I don't see the raise hand in that at the moment. Is that because I'm this? Oh yeah, raise hand, it's at the bottom of that emoticon thing. So yeah, reactions, raise hand if you want to talk. However, we're not expecting people to talk until after the main presentation. So please feel free, and I encourage you to write questions that you have into the chat box during the presentation, because when it's over, the first thing we're going to do is look through those questions and send them, ask Ken to answer some of those, and then we'll go live for more interaction. Hopefully we'll have plenty of time because Ken's going to be has a wonderfully clear and organized presentation for you, and we'll have lots of time to interact afterwards. So Ken Carloni, I first did a biochar workshop with him 3 years ago with him in Kelpie, which was wonderful. And it set me on this course of biochar forestry stewardship. So I'm really excited to have him with us tonight. And I don't have his bio in front of me, but hopefully you all read it when you were considering coming. That he is one of our wonderful experts. And I'm going to hand it on over to you, Ken, now.
Okay. Well, I am Ken Carloni, and I will share a screen here. And okay, can you all see that?
Looking good, Ken.
Okay. Had an odd little green line on mine here, but that's all right. So anyway, just a little bit of background, in case you haven't read the bio. I got my original, my master's from when I was a youngster, was in pollination biology. But then I came west at the tender age of 25. And I've been here ever since in Oregon, and there I became interested in forest ecology and got a PhD from OSU, focused on forest ecology, but particularly on the use of landscape fire by the native folks and the indigenous folks in this area, and then started hearing more and more about biochar, and was really pulled in to that sphere, mostly because of its ability to capture carbon and as a way to store carbon against climate change. So that's what sort of put me on this path. And there we go. So the biochar work that I've done for the most part, except for workshops and so on, as far as the landscape level work that we've been doing, is at Yew Creek, which is in southern Douglas County, just west of the town of Riddle, if you guys are familiar with the area. And our mission there, it's a nonprofit, and is to conserve and restore historic habitats and native biodiversity while generating high quality goods and ecological services from our lands. These activities will create unique opportunities for research, training, education, recreation for participants of all ages. And so just to give you sort of the way we're approaching this is that restoration comes first, and logs on log trucks come second. Okay, so the logs that we generate from this property, and we estimate that we're growing about 75,000 board feet a year on this 380 acres. I failed to mention, and so we hope to be able to provide a couple of jobs, into perpetuity, harvesting and milling that timber, but again, always driven with the focus that we are improving habitat for spotted owls that have moved back on to into the area. If you were to turn around in that photo and look backwards, you would see an old growth forest, which is unfortunately not on our property. And if it was, it wouldn't be an old growth forest, it would have been logged. It's on BLM property, and because we're part of the barred owl experimental removal program, which means that experts with shotguns have come in and taken out the barred owls, we've got spotted owls have moved back in and have successfully produced offspring in the forest. So our goal is to take the remnants of that old growth stand to the north, a little chunk to the southeast corner, and another chunk on the west, and knit those together so that we create more habitat for spotted owl and other old growth dependent species. So as we'll see, all of the thinning that we're doing is thinning from below. We're taking the smallest stems and leaving the biggest trees out there, with the idea that we're going to accelerate the production of old growth forest to recover from this ranch that was entirely logged of anything merchantable as far as conifer was concerned by the end of the 1960s. Fortunately, though, the giant madrones and the giant old oaks on the property never had any value. And so that's what our main focus is, to restore oak habitat and native pine habitat. But we're also, we've got the biggest tree on the property is a 6-foot diameter madrone. So we're very, very happy with them. And we're trying to clear the encroaching conifers out, because with the absence of grazing and the absence of burning, conifers are winning over these centuries old hardwood trees. So we're trying to keep those old timers on the stump. So launching into our discussion, first of all, what is biochar? The International Biochar Initiative defines it as the solid material obtained from the thermochemical conversion of biomass in an oxygen-limited environment. So basically, we're baking wood in the absence of oxygen, a process known as slow pyrolysis. And where does the bio part? I mean, that's just charcoal. That's been being done for thousands of years, right? For people to run their forges and blacksmith shops and so on, right? So what is it? When does it become biochar? And the answer is, when it goes into the soil, it becomes very biologically active. And so sitting in a pile right after you've dumped it out of your kiln, okay, it's charcoal. But as soon as it gets introduced into the soil, all kinds of magic happens. And we'll talk about that here coming up. And that's biochar. And as I mentioned earlier, and what really drew me into the whole biochar world is the fact that, for reasons I'll explain here shortly, the form of carbon that biochar contains after that thermochemical conversion is extremely difficult for microbes to break into, and therefore it has a half-life of over 1,000 years in the soil. So once it goes into the soil, for all intents and purposes, it is, sequestered. So that really drew me to getting involved in biochar. So why make biochar? Well, first of all, many of us who are doing forest management, when you thin those, when we're thinning those trees out and they have no value, the small trees, well, they just lie on the ground and become hazardous fuel for any kind of ignition that might happen in that area. So we have to remove those or do something to reduce the hazard of that very flammable fuel that's down on the ground. Once, as I mentioned, once that biochar gets into the soil, it improves soil productivity, therefore increases photosynthesis, therefore captures more biomass, right? So if you improve the soil, you improve growth, you capture more carbon. So not only does that carbon that you've made into biochar stay in the soil, but it also promotes the growth of the forest and the greater capture of carbon. Retains water and nutrients, and we'll talk about why. It also decreases smoke and greenhouse gases relative to the other fates of that material. So if you just left that material on the ground, it would slowly decompose and release that carbon into the atmosphere. If you do what is most commonly done, and pile it up and burn it, it almost instantly becomes carbon dioxide with very little char left over in the end. And then, of course, we talked about the long-term carbon sequestration. So I'm going to organize this talk. I'm going to just a little bit of history of biochar. And then we'll talk about the science of biochar and the technology of biochar. Those will be the two main chunks of the talk. And then at the end, we'll talk about National Resource Conservation Service funding that's available for folks that own timberland to be able to get some funding from the government to create biochar. So as far as the history is concerned, back in the 1870s, soil scientists that were beginning to work in the Amazon discovered these very dark, very rich, highly productive soils. And as most of you know, in tropical forests, there's a real challenge in if you remove vegetation from the soil, that soil leaches very quickly and becomes very nutrient poor. And it takes a long time for those soils to recover. In Northwest forests, about 50% of the biomass is above ground and 50% is below ground, because we have a whole season, several months, where growth doesn't really happen very much. Life slows down, right, in the winter months. Whereas in the tropics, when the temperatures are fairly warm most of the year, the soil microbes are constantly working. And so in the typical tropical forest, you've got about 90% of your biomass above ground and about 10% below ground. So when you cut off that, those trees, you only have a very small bank account left in the soil. And so they leach very quickly and they lose productivity fast. But when the original soil scientists discovered these soils, they thought they were volcanic soils. They classified them as even separate soil classifications. But later on, only in the last couple of decades, people came to understand that it was just carbon in these other types of soils. And so if you look at, you can all see my cursor, okay, I hope, right? Pointing around here, good, thanks. So you see here, these lines say how much carbon soil organic material, is soil organic carbon is in the ground. And you can see the soil from adjacent, has very little carbon in it, whereas the terra preta soil is a lot of carbon, very little carbon, a lot of carbon, very little carbon. These are all different kinds of soils, but when you add the charcoal to them, they become productive and stay productive. Some of these soils were built as far back as 2,500 years ago by the indigenous people that lived there. And only recently have soil scientists discovered that these are, quote unquote, anthropogenic soils. These were created by humans and have maintained their productivity for all of these years. And, we tend to think about terra preta soils and high charcoal soils as being, these Amazonian soils, but the Midwestern, the US, the great prairies of the Midwest have very high levels of charcoal in them because of the frequent burning that the indigenous people of that area did. And when these light fires would run over the surface, the heat would penetrate the soil, but not the oxygen. And so the little bits of organic material, again, would get pyrolyzed, not combusted, right? Pyrolyzed and baked into charcoal. And even here in the Pacific Northwest, this is a sketch that was made in 1841 in the South Umpqua. And you notice this big pall of smoke rising in the background because fall was when all of the Willamette Valley, all of the Umpqua Valley, the Rogue Valley, and on down, Sacramento Valley and so on, all these vast grasslands were burned almost every year. And this has been very well documented. And the next day, the same sketch artist who was Henry Eld, who was with the Emmons expedition or the Wilkes expedition, continued south, and they're just crossing the quote unquote Umpqua Mountains over into the Rogue where many of you folks are located. And notice that there are the burnt small burnt trees on the top of the ridge, a pall of smoke coming up, somebody's burning out their camp down below. And so fire was, it's being well accepted now that fire was used to maintain these open grasslands. But only recently have people come to understand that the Native Americans carried fire everywhere across the landscapes where they were traveling and hunting and gathering and so on. And so fire was the big medicine that got the job done. Stone axes didn't clear the roads on the ridges, fire did, right? And so there was a constant input of charcoal into the soils. And so if you think about it, for the last, the better part of the last century, we've suppressed fires, and therefore these pulses of charcoal that would normally have been going into the soil on a regular basis have not been. Now we're getting our comeuppance now, right? The forest is resetting after 90 or 100 years of fire suppression. And so there's a whole other discussion there we could have about how landscapes have changed and how much more fire prone they are, and how climate is changing the ability of fires to blow through these forests. So soil carbon loss is global. And so biochar can help to reverse that trend. So I'd like to spend a minute with this slide. This is a slide that I made for my students. I guess I forgot to mention in the opening bio there that I taught biology and natural resources at Umpqua Community College for 31 years. And to help my students understand the hierarchy of life, I created this little graphic where at the molecular level, things are small and they're moving fast, right? So we've got nanometer things moving in nanoseconds. And as we take molecules and turn them into organisms, we might be talking about phenomena happening in seconds, right? And in populations where we take groups of organisms and put them together, things are going on the order of years, maybe, and then communities, centuries, landscapes, maybe thousands of years, and so on, till we get to the biosphere, which is 4.5 billion years and still going, right? So on the other side of this are the emergent properties that happen when you mix systems from the previous level, from the lower level up into the higher level. And so those are properties that are unpredictable based on what you know about the previous level. So for example, you can know everything there is to know about a carbon atom. You can know everything there is to know about an oxygen atom, but you could never know what carbon dioxide behaves like, right? And because until you put those things together, those new properties don't emerge. So as you build these levels up and up and up from small and fast to big and slow, you see these new properties that emerge at every step of the way. And I set it up this way because this is how I talk about the science of biochar, from small and fast to large and slow, because biochar has effects at all of those levels. Okay, so let's look at some of those. So looking at the science, at least the part of the science that I'm going to talk about, again, starting at those smaller levels and moving up, we have to talk a little bit about chemical bonding patterns before we understand how biochar, is constructed and why it works the way it does in the soil. And then we can look at the molecular, or really the macromolecular structure of biochar. And then we can look at how that affects soil microbial ecology and how that in turn affects the next level up, which is forest ecology, right? So how do those microbes move energy and nutrients through the system to the benefit of plants? And then ultimately the global carbon cycle is affected from the very smallest levels on up. So first of all, just and hopefully, nobody gets, flashbacks from their, high school chemistry class, and, it starts to quake and shiver here. But a couple of things we need to understand I'm going to start over here, first of all, with covalent bonds, because those are the strongest bonds. They're shared electrons. Those are the kinds of bonds that hold things together. So all of these shared electrons make these very stable bonds that give life its shape and structure. Moving backwards to ionic compounds, really as biologists, as natural resources people, we're much more interested in ionic compounds when they get dissolved in water, right? I mean, crystals are interesting, and those sorts of structures, and geologists are very interested in ionic compounds. From a biological standpoint, we want to know what happens to these things when they dissolve in water, especially in the soil solution, right? So it's the classic situation. You take salt and you drop it in water, and the sodium chloride, which is this nice little square crystal of salt, dissociates in the water. And it turns out that the chlorine swipes one of the electrons from the sodium and becomes negatively charged. It has one extra electron relative to its proton. So it is an anion, okay? It's negatively charged. And since the sodium has lost an electron, it has one more proton than electron, so it's positively charged. And these charges of these ions in the soil is what causes them to either move through the soil or be adsorbed onto surfaces where they remain available for plants and microorganisms to take up and use in their metabolism. Hydrogen bonding here is the attraction between water molecules. And I won't go into the details too much of dipoles and things like that, but the reason that a water droplet will turn into a little sphere as it's falling through, or that a water strider can stand on the surface of the water, is because each molecule has a slight attraction. The hydrogens have a slight positive attraction, the oxygens have a slight negative attraction, and that causes them to stick together. And again, this is important when we talk about water holding capacity of biochar, that those slight charges on the surface of water molecules are what drives that process. And then another thing that's kind of interesting where biochar is concerned is that, as we'll see in a moment, the way those carbon molecules are strung together, it creates these little slots of free electrons between them. And so you may have been reading here and there about how graphene, which is the major component of biochar, is used as used in the semiconductor industry because they actually conduct electricity. And as we'll see, they're part of this tiny little but vast but highly expansive underground electrical grid that's in the soil. And this is brand new stuff. This is stuff that has only been coming out over the last really less than a decade, our understanding of how important those interactions are. Okay, so armed with that information, let's take a look at pH, acids, bases, and salts, because we talked about the fact that that biochar can mitigate soil pH, right? Well, how does that happen? A lot of us, talk about pH, and we know there's certain things go on with acids and bases and stuff, but really kind of dialing into why that happens is important to understand how biochar frees up, in many cases, nutrients in the soil to become available to plants and microbes in the soil. And so pH, it's very frustrating because it is the negative log of the hydrogen ion concentration, which is really frustrating, because lower pH means more protons, more hydrogen ions, and therefore the solution is more acid. And so when the number is low, the number of protons are high, and it means it's more acidic. So it's very annoying. It's also the log function, which means that pH 6 has 10 times more hydrogen ions in it than pH 5. Sorry, I just went backwards. I just did it. Okay. The pH 6 has 10 times more hydrogen ions in it than pH 7. pH 5 has 100 times more than pH 7. So again, we looked before, before it was sodium chloride, we dropped that in water, it dissociated into the cation and the anion. Well, acids do the same thing. But in this case, we call them an acid because the cation in this case is a hydrogen ion. Okay. And I just referred to them as protons a moment ago, right? So if you remember back and looking up at the big periodic table on the wall in front of your chemistry class, in the very upper left-hand corner, you saw hydrogen, right? Because the hydrogen atom is a single proton with a single electron around it. Once that electron gets taken away by in this case, hydrochloric acid, chlorine, it is now just a single protein. So hydrogen ion, proton, and H with a little plus next to it all mean the same thing. Okay. On the other side of the story is our bases. And bases are so called because acids are acids because when they dissociate, they release a proton into solution. Bases are defined as those materials that will take up that hydrogen. So you notice there's a hydrogen over here. If you drop that in here, that hydrogen would join with that hydroxyl ion and become H2O again. So how many protons are out in solution, or how many are being bound up by other molecules or other surfaces in the soil is what's going to determine soil pH. And as we'll see, that has an important effect on the availability of nutrients in the soil. Okay. So what happens when you cook wood in the absence of oxygen? Okay, when you pyrolyze that wood. And again, I'm making the distinction here between combustion and pyrolysis, because combustion, complete combustion of biomass, all you're going to have left over is pure, white or gray ash. Only the mineral material is going to be left. And all of those carbon atoms that are in that wood will have combined with oxygens or hydrogens to become various gases, greenhouse gases. So we're interested in slow pyrolysis. We want that wood to cook, but not to lose or to try and hang on to as much as that carbon as possible. And so you notice here that wood is composed of lignin and cellulose. And you can see that both of those have ring structures associated with them. And when you heat them in the absence of oxygen, they condense into these sheets of graphene, little honeycombs. But the interesting thing here is that you don't lose the architecture of the cell wall structure in that char. And so you see all the little tiny chambers that the cell walls of this actual wood have in them are converted to the same kind of chambers. I mean, they condense, they shrink a little bit, but there's still an enormous surface area. So that's one of the, special powers that that biochar has, is very high surface area. And it also has a very dense charged surface, which we'll talk about in a second. But notice that all of these are very condensed now into these sheets of graphene. And the other thing, if you look over here, the carbon atom requires 4 bonds to have all of its outer shell satisfied, okay? And so it requires 4 things to be stuck to it, right? But what do you see here? You see 3 things stuck to it. But what you see are these little double lines here, and those are double bonds. And so even though you only see 3 axes sticking out from the carbon molecules here at all these apices, some of those are double bonds, so that every carbon atom has 4 sets of bonds, even though it's only stuck to 3 things. So that makes it very difficult for microbes to get in there with enzymes and cut those pieces apart, right? So carbon's a great, I mean, we're all based on carbon, living things, right? It'd be absolutely, that's the bedrock of our molecular structure. We all have to have carbon, and microbes would love to have that carbon, but it's just that it's bound up in such a tight configuration. It's very difficult for their enzymes to break those bonds so that they can use it in their metabolism. So it turns out that if you just have regular biochar chunks of wood here, they're going to decompose quite, fairly rapidly. Needles and twigs and small wood that falls out of the forest every year generally has a life in the, on the surface, the duff on the surface of something like, 3 to 5 years before the microbes completely dismantle all those carbons and use it in their own metabolism. And then they respire just like we do and release that carbon back to the atmosphere. So when you carbonize, when you pyrolyze that biomass, it turns into those ring structures that the microbes can't break down, and therefore it lasts in the soil for, the calculations are something in excess, the half-life is in excess of 1,000 years. So once that char goes into the soil, it's sequestered. Even more so than tying carbon up in a tree. What's the longest a tree is going to live? 700-800 years for a Doug fir, something like that. And it's eventually going to decompose, and but this stuff is not. And so as far as biochar and the soil microbial ecology is concerned, biochar is an excellent substrate for beneficial microbes. So the microbes that are in there helping the plants, that are in mutualistic associations, win-win situations with the plants, are being encouraged by char. And the root rots and the denitrifying bacteria and the things like that are not a help to the system are discouraged. And this electron exchange capacity, which I'll talk about in a minute, water retention, as we've mentioned before, nutrients as far as the ion exchange capacity, the surface of that, pH mitigation, and soil structure, how the soil, how the pores in the soil actually form. All of those things are promoted by biochar. So certainly habitat for mycorrhizae and the plant growth promoting rhizobacteria are in very important functions of biochar. And then here's this crazy situation here where these sheets of graphene act more like a metal. They're a conductor. And so remember we said that that each carbon is supposed to have 4 bonds, but we only see 3 there. And it turns out that those double bonds, electrons can't occupy the same space. So what they do is they flip up and they flip down. And so in between those sheets of graphene, there are these fields of free electrons. And the crazy thing is that some organisms are looking for electrons because, remember, that's the molecular glue that holds atoms together into covalent bonds. You need electrons to stick those atoms together into complex molecules. Other organisms are using what are called electron transport chains to pull energy out of those covalent bonds, and they need a place to dump those electrons. So it turns out that biochar acts as a geobattery in the soil, picking up free electrons from electron transport chains of organisms that are dumping their electrons, and making those electrons available to other organisms who need them to build their macromolecules. So it's this crazy, like literally an electrical grid that goes on underground with these electrons flowing through these little bits of biochar from one microbe to another. Just fascinating stuff. Okay, so remember all those micropores that we saw in the biochar? Well, not only are they pores that can hold that water, but that charged surface attracts the water. And once water sticks to something, other water molecules will stick to those molecules. And so you wind up with this film of water that coats not only the surface of the biochar, but the surfaces of all of those interior pores. And so in a experiment that was done in a drought year in 2012 in Iowa, plots with biochar in them had 15% better water retention. So that biochar hangs on to the water, holds it, keeps it from leaching out of the soil. And not only does it hold the water, but it hangs on to all of the ions that are dissolved in that water. So biochar and soil pH, high temperature biochar, or at least, we shoot to, from that 450 to 550 degree range for making biochar. And I'll talk a little bit more about that when we talk about nuts and bolts of the technology. It's alkaline and it's, around pH 8 or 9, which is fairly high. Part of that is because a lot of the ash that's produced along with the biochar, there are a lot of hydroxides in that, potassium hydroxide and sodium hydroxide and those sorts of things that are going to be grabbing protons out of the soil and therefore increasing the alkalinity of the soil and therefore the pH of the soil, right? Low temp biochar is closer to neutral because there's less ash. There are also more organic acids left over, and low temperature biochar, or what we call torrified wood, you've all sort of seen that where it's an incompletely burned piece of char. It's just kind of brownish color. It's partly pyrolyzed, but there are still a lot of resins and oils left in it that actually make that particle hydrophobic. It actually will repel water. So that's not really what you want, right? You want char that has most of that stuff burned out, that has that really nice, huge charged surface so that it can stick water and stick nutrients to itself. Now, if you're in a situation where you have alkaline soils, fortunately, mostly here in the West, our soils tend to be more acid. And so adding biochar to the soil is actually going to help, mitigate those acid soils. If you're in a situation where you have alkaline soils, you can neutralize them, neutralize the char by composting with organics that will adsorb those organic acids. So composting, manure tea, compost tea will provide the organic acids that will counteract that alkalinity. You can rinse the ash away with water, or you can leach outdoors during the rainy season. Just leave your pile of char open to the rain. Nothing's going to happen to that char. It will not break down in that pile, but you can just let the rain leach that ash away and decrease the pH of that, make it more acid. You can use acidifying fertilizers, ammonium, urea, urine charged in a lot of parts of the world. Folks will charge the biochar with urine and night soil. And then acidifiers like acetic acid or citric acid or sulfur. And I have a little asterisk down here if you want to read more about sulfur. There's a reference here. Or in some cases used to adsorb hydrogen sulfide in lagoon and anaerobic digesters. So in those sorts of situations, if you are adjacent to that kind of activity, you can acidify that. But mostly here in the Northwest, and I assume that most of you are tuning in from somewhere in the West, we don't really have to worry about that too much. Because our soils tend to be on the acid side anyway. And so as far as the adsorptive surface for nutrients to adhere to, I'm not going to, this is kind of a little complicated graphic, and I'll just kind of give you the sort of the 30,000 foot discussion of this, that biochar, depending on the pH, depending on whether there are lots of hydrogens in the environment or few hydrogens in the environment, you can have these radical groups, these parts of organic molecules that stick out of the surface that are going to give that biochar particle different chemical properties. And so since the charge surface of biochar is mostly because of those electrons that are floating up and down below those layers, grabbing onto cations is something that biochar does really well. So these are positively charged: ammonium, calcium, magnesium, iron, manganese, things like that. Those are positively charged, and they'll stick to the char right away. But that doesn't mean that negatively charged things won't, because once those positively charged things stick, there are these slight positive charges that negatively charged anions can get associated with. So even though it's the cation exchange property of char is really the main function of how it hangs on to and releases nutrients, anions can be bound to it as well, especially when there's changes in pH will change char's ability to hang on to different soil nutrients depending on the functional groups of the organic acids that stick all over it. Okay, and so another place where biochar is really useful is in mine tailing restoration work, because most of the metals, the heavy metals that are coming out of mines and old abandoned mines are cations. They're positively charged, and so biochar can be used to clean up some of these sites. And so that's something that I think we're going to see more and more of in some of these super fun sites that are horribly polluted with chromium and and various other heavy metals, arsenic and things like that. Okay, so again, why do we care about pH? It turns out that various nutrients in the soil are dependent upon pH. So they become many of the most important ones: nitrogen, phosphorus, potassium, sulfur, calcium, magnesium, the big important nutrients are most available in the relatively neutral area. Manganese and boron, copper and zinc fade into that area. Iron's a little trickier because it's really more available as the soil becomes more acid. But the fact that it is a cation, and so it can bind to the char in the soil, even if it's very neutral or even slightly alkaline, will still hang on to whatever iron ions have dissociated and are available in the soil solution. And then soil structure is incredibly important. You all know that you can have the greatest soil in the world, but if you run over and over and over with a tractor or something and you compact it, you lose it. The oxygen can't diffuse in, CO2 can't diffuse out, and you wind up with anaerobic soils. And that is, basically, it is not habitable for aerobic organisms. And the anaerobes that would like to inhabit it, are generally not what we want in our soil. They're antagonistic to plant growth. They're antagonistic to beneficial microbes. And so it turns out that because char is so good at adsorbing all these things to the surface, it will also adsorb bits of clay particles and that sort of thing and become aggregates. And so you see those spaces around here become spaces for water to percolate through and oxygen to diffuse into and carbon dioxide to diffuse out of. And so this is why we, get out our spading forks and if you do that kind of thing, or keep our soils from being compacted. Back in the day when, you used to till up your soil all the time. Now we're starting to understand that that's not such a great idea. You're better off letting the microinvertebrates aerate your soil, keep a mulch on it and stay off of it, than digging it up. Because every time you open up the soil, you expose that soil to oxygen and organisms that are going to metabolize that soil. Organic carbon will do that. And so you'll bleed a bunch of carbon dioxide and you'll lose soil organic carbon, and you'll bleed a bunch of that carbon dioxide into the atmosphere. And so that's why no-till farming is becoming more and more common. And that's why the less you can disturb the soil generally, the better, unless it is compacted. And then, then break it up. But if it's not compacted, don't mess with it. So now we've kind of worked our way up to our, larger scale, hierarchical scale to forest ecology, and biochar plays an integral role here too. This is a chart. This is going back, almost a half a billion years when plants first show up. So earliest vascular plants show up, and 10 million years later, our first evidence of fire, right? And so as forests become more widespread, forests increase, fire increases, oxygen goes up, fire increases. So the interesting thing here is that biomass and fires have interacted with each other since there were plants, since organisms moved out of the ocean and plants moved onto land and forests began to form, fires followed. So that means that forests and fires co-evolved, but they both co-evolve. Well, the forest also co-evolve with biochar. And so biochar is not anything new. It's been in the soil. It's been added to the soil for hundreds of millions of years. And so it's a very integral part of what happens in soils almost everywhere on the planet. So again, I won't go into all the details of this gnarly diagram here, but I want you to notice the phosphorus cycle, carbon cycle, and nitrogen cycle, and look at where all the arrows are going through ectomycorrhizae, through mycorrhizal fungi. And probably most of you know that these are the good guy fungi that will attach themselves to plant roots and increase the surface area for the absorption of water and minerals from the soil by the plant. And in return, the plant sends sugar down that it's made for photosynthesis. So it's very much of a mutualism. The fungi wins by getting food from the plant, sugar from the plant, and the plant wins by increasing its surface area and getting more water and minerals. It's an absolutely critical function in something like 90% of the plants in the world. And as scientists paleoecologists have gone back into the fossil record and sliced through some of the roots of these ancient plants, they find mycorrhizae associated with them. And so it is a very ancient mutualism. Some evolutionists believe that the ability for plants to even invade land was because they invaded as a partnership with fungi that were originally parasitizing them in the oceans, but became mutualists when they wound up in the estuaries and they would dry out, daily with the tides or seasonally with rainfall. And so that relationship between mycorrhizae and plants goes back as far as plant growth goes back. And that relationship between plants and char goes back almost as far back as plants go back. And so char has been in the soil. It's been an integral part of that mutualism between mycorrhizae and plants since there were mycorrhizae in plants. So how does forest structure affect, or how does the temperature of fire, and in a minute, how does forest structures affect on fire and the temperatures of fire affect biochar in the soil. And so we talk about wildfire, but we also have wild pyrolysis out there too, because not everything is burning up completely. Fires produce a lot of char, but ground fires, lower temperature fires that are creeping around the forest floor are burning at lower temperatures, maxing out at about 800 degrees Celsius. And remember, our biochar optimum is somewhere between 450 and 500. So these kinds of fires are really producing the kind of biochar that we're the most interested in. Whereas these fire nados that form in plantations, and this was a photograph from the Douglas Complex fire that burned just to the south of Yew Creek back in 2013. Crown fires produce much higher temperatures, 1,200 degrees Celsius, and unfortunately, therefore, before I get to this slide here, okay. How does temperature affect the biochar? Here again is that sweet spot, right, that we were talking about. But higher temperature biochar will, has a greater cation exchange capacity. Its surface area goes up, its volume goes down because more of it's turning into greenhouse gas. But there are some, it's better at holding on to anions in its higher temperature. So what you really want is you want a range of temperatures to produce bits of biochar that are going to behave in a range of ways. And that will kind of cover most of your molecular bases there. And so what I wanted to show you here was the difference between, this is that forest that I told you that if we had turned around in that first slide and looked backwards, that's this forest right here. And the spotted owls are nesting right back in here. This is a Roseburg Forest Products plantation right here. And you can just see clearly that it's not about fuel volume. Fire is not driven by fuel volume. Fire is driven by fuel structure. And so every one of these crowns is touching. A fire that gets into that crown is going to burn from one side to the other without, and it's just going to burn through the crown and not on the floor. It gets to forests like this, where the crowns are far apart, it's very chaotic, and those tend to generate ground fires. The old timers used to refer to old growth forest as the asbestos forests, right? Because they didn't burn with anything like the severity of plantations. These are that Douglas Complex fire that I told you about before, where I showed you the picture of the fire tornado. This is what those plantations look like after the fire. They just look like the hair on the back of a dog, right? And the only green left on the landscape are the old growth forests in the patches of BLM. This burned through BLM checkerboard, and so every other square mile is public, private, public, private. So the only survivors here were the old growth forests. And if you look here before the fire and you look and see where the plantations were, you look and see where the hottest fires were. And, and I didn't cherry pick this stuff. I mean, you could, here's another plantation here, and here's a hot spot over here. Here's another plantation right here. There's a hot spot here. Everywhere you go on this map and you look at the old plantations, you see a hot spot that the satellites picked up when they were looking at fire intensity, right? The heat coming off the ground. Fire severity is how much mortality you have. Generally, they're the same. The amount of intensity means the amount of, you're going to get the amount of mortality. But in some of the cases where you see these like mid intensity, you say, oh, well, that stand must have partially burned. Well, if it's a plantation of 6 foot tall trees, it just doesn't have the fuel to generate that kind of heat. So in some cases, lower temperature, lower intensities, lower temperature fires can produce just as high mortality if all of the trees are small. So forest structure, wildfire, and biochar quality and quantity in plantations, you've got homogeneous fuels. They're more flashy. They carry fires better, more high mortality crown fires, higher temperature fires, therefore less char, more CO2, and higher pH char, because as I mentioned before, the higher temperature that you create the char, the higher the pH as well. So that's not necessarily a bad thing. In mature forest, you have a chaotic fuel structure, more large, slow burning fuels, more low mortality ground fires, lower to mixed severity or intensity fires, more char, less CO2, and a greater pH range of the char, and a greater range of chemical characteristics and therefore biological characteristics of that char. So that's why this was what the southern edge of our property at Yew Creek looked like in when this Google Earth image was taken in 2015. And down right along the edge here, we have, and this is all, as I mentioned before, by the end of the 1960s, when the original ranch went bankrupt, every stick of conifer that had any value was cut. Again, we're lucky in that the hardwoods never had any value, so they're still there. So this is 60-year-old second growth. Fortunately, you can tell kind of by it's not super uniform because it was never replanted. This was logged right before the Forest Practices Act came in, and they didn't have to replant, and they were going bankrupt anyway, so they didn't. So we're lucky. This is all native genetics here. So we don't have soldier rows of 10 by 10 off-site Douglas fir. You know, we're lucky in that we have some genetic integrity here. But just down here is this wicked flammable, another Roseburg Forest Products plantation that is just a tinderbox. So the first phase of the work that we did, this is the same shot. And so you can see now we've created, here's that edge of the Roseburg Forest Products plantation. Now we've got a couple of 100 feet or 100 feet to a couple of 100 feet of an area in there. And this is the ridge, the road on the ridge. We have a chance to stop a fire right there if it comes up from the south. And if it does, and it gets into our plantation, notice how we've got our crowns separated here, right? Compared to that. And then this area in here, you know, we've really opened that up along in here. So what we've done is we've opened up those stands, but we've thinned from below. We've taken the smallest stems out and left the biggest trees in the stand, because our primary goal is not to make the fastest buck we can, in which case we just cut the big trees. Our primary goal is to produce high grade habitat. And so we think this is the best way to do that. And so people say, well, geez, you just took a whole bunch of that and half of the carbon, you know, went up into CO2 as you're cooking the other carbon into biochar. And that is true that initially biochar production is carbon positive. We put more carbon into the air in a short period of time, but over the long term, it's carbon negative for a couple of reasons. And first, we use and we'll talk about this when I talk about how to load and fire kilns. It turns out that most of the carbon that we lose in carbon dioxide and other potential greenhouse gases are from the fine fuels that would have decomposed in the forest over the next 3 to 5 years anyway. So we use short cycle carbon to char the larger diameter stuff and put it into the ground permanently. So everybody talks about the weather, but nobody does anything about it. Okay, so let's do something about it. So let's move from our science discussion to our technology discussion. So integrated on-site biochar production, that's what I call what we do. We integrate biochar production into our forest management practices, and we use that char on site. We don't take it off site. So I'm going to start talking, I'll talk to you a little bit about flame cap kiln design and fabrication. There are a couple of options for you to buy kilns, but those of you who are, creative, have some skills, have some scrap metal around, can make your own. And then we'll talk about kiln operations, safety first, feedstock handling, loading, firing, continuous feeding, and then quenching. So a little bit about flame cap physics. The kinds of kilns we use are flame cap kilns, meaning that you put the larger material on the bottom, the finer fuel on the top, exactly the opposite you would build a fire in your fireplace or a campfire or something, right? And because what you want is you want that flame cap to burn continuously on the top, because convected heat goes up, but radiant heat goes in all directions. It's like standing in front of a wood stove, right? You feel the heat coming off the side of the stove. And then of course, convected air goes up from the top of the stove. And so that's the basic principle here. You want, in any kiln design you have, or any kiln operation, you want to maintain an even flame across the entire top, because it creates a flame cap. That convected air that rises pushes oxygen away from the surface. So there's enough oxygen coming in from the side to feed that flame on the surface, but that radiated heat that goes down into that low oxygen environment at the bottom carbonizes, pyrolyzes that char down below. So you blow off about half of your carbon into the atmosphere to cook the other half of the carbon and put it in the soil for 1,000 years. So design considerations, materials, fabrication, efficiency, portability, and then modularity and scalability. Okay, so you want materials that are going to last. You want to be able to fabricate this thing as cheaply but as effectively as possible. You want it to be a high efficiency kiln. You want to be able to move this thing around, not only on a pickup truck from one place to the other, but when you're busting hump out in some gnarly patch of ground out there, you need to be able to move a kiln around in the forest, without killing yourself. And so in the big wide open spaces in Utah, Darren McAvoy and others are making these huge kilns, and that's all great. But when you're busting it through a forest and you're, walking up and down a 50% slope or something, you need something that is of human scale, that you can move around as a human. So materials, durability, steel, mostly 20 gauge or heavier. The heavier gauge you go, though, the heavier in weight you get. So again, that portability issue becomes a problem. Has to withstand about 800 degrees Celsius. So you can't use aluminum rivets because they'll melt. So you have to pay a little bit of attention to that. And of course, cost and availability. Steel tariffs are killing us right now. Talk to Kelpie Wilson about trying to sell her kilns. Jesus, she's just being killed by not only the tariffs, which hit us a couple of years ago, but now steel has continued to rise as the cost of building materials rose. Lumber went up, it came down. Steel went up, it didn't come down. So if you have a source of salvage material, and a little creativity, that's a good way to go. And then salvage, seconds, recycled. Fabrication, welding is the most costly. It takes people who know what they're doing, but if you have those skills, then that's great. I've been doing some spot welding lately. You can buy a cheap spot welder at Harbor Freight for $150. So that can go into your toolbox where you might never have thought about welding before, in terms of, stick welding or wire welding or something like that. Screws, you can hold the things together with them. Self-tapping versus pre-drilling. You have to think about the labor involved in that. Rivets are great. I would use rivets on everything, but they're time consuming and labor intensive. So your labor costs really go up when you're riveting, and you can get steel pop rivets. So that works. And then the only shop work that I require is the cutting and the break work, the bending of the sheets of metal. So I have to go down to the steel fabric, to the metal shop, and get them to bend the metal for me. And then I put the rest of it together in my shop. Efficiency, surface to volume ratio. How much surface is there for the volume of the kiln. There have been no formal studies of this, but in talking with Kelpie and some of the other folks that design and build kilns and use them, we figure the sweet spot is about 0.3. So for every cubic foot you have in your kiln, there should be about 1/3 of a cubic foot on the surface. Higher values, meaning that there's more surface and less volume, means you're going to get more ash and less char because there's more oxygen can hit more of that fuel. Whereas lower values, if you have too small a surface and too much volume, you're going to wind up getting uncharred wood. Maybe more uncharred wood than you want, or you're going to have to leave that flame cap burning for so long that you're going to lose that fuel. So that sweet spot tends to be right around 0.3. And then, of course, minimizing oxygen infiltration. All the joints must be tight, especially low down in the kiln where your pyrolysis is happening. And then sheet steel can buckle. So if you don't put enough fasteners in if you're using a frame, you can wind up with buckling and oxygen leaks through where the steel buckles. And then single wall versus double wall. Kelpie's new kiln is a double wall. My design is a double wall. And what happens there is that when you have a slot low down on the outside and a slot high up on the inside, the air enters between the walls of the kiln, travels up the kiln and then back into the kiln. So it carries the heat back into the kiln. And so you don't have as much heat loss. More heat that stays in the kiln, more efficient pyrolysis. Okay, and I'll show you some of those designs here coming up. Portability and modularity. Module size and weight, you need to scale it to human labor. Less than 50 pounds is ideal. And anything over 48 inches high takes a huge amount of extra energy. You wouldn't think 8 inches would make a big difference loading a kiln, but it does. I like my kilns at 40 inches. I'm a 5'7" guy. And so a taller person can load that kiln just as easily, but a shorter person, especially women in the field, that lower edge of that kiln, you would be amazed at how much less energy it takes to load a 40-inch high kiln than a 48-inch high kiln. And then, minimize the mechanization required unless, again, you're out in the open spaces, you can move tractors through the landscape, great. Big kilns, mechanized, that's great. But if you're out there with a bunch of labor, that all of that stuff is important. You need to, this is a very much of a human labor driven, human scale enterprise. Compact and stackable is good, either nesting and stackable. Scaled to a standard pickup truck bed is good. And then module numbers and articulation. If you have modules that can go together in any number, then you have an infinitely expandable kiln. So you can size it to small jobs, medium jobs, large jobs. How much labor do you have? It takes more labor to feed a large kiln continuously and keep that flame cap going than smaller kilns. And then also, if those panels articulate, you can build your kiln to fit your material and to fit the terrain you're on. So I'll show you some pictures of that in a bit. Okay, so flame cap kiln designs, they're all over the place. This is the Wild West right now. This is the ground floor. So small DIY design, 55-gallon drums are really, are commonly used. They're cheap. They're all over the place. Low skill construction, but they're small scale. You got to have a lot of them to do a larger project. They're great for backyard, occasional biochar. They have very high surface to volume ratios, so their efficiency is very low. You have to dice up your feedstock into very small pieces to fit it in, so there's more labor. So you have a high labor to output ratio with those. This is a kiln that I designed for a project on Guam where, you know, islands, military islands are just swarming in 55-gallon drums. So I created this little daisy chain design so that you just use the barrels as walls of the kiln, and they're as expandable as you want them to be. I just use box rail hardware for like rolling barn doors, and then little pins at the bottom, pins at the top, and that keeps air from leaking in where the ribs of the barrels are. So it has a very low surface to volume ratio. It's hard to seal in between, but I think, you know, you make up for that by that good surface to volume ratio, and you see how that flame curls around from inside those barrels, and so it keeps air from infiltrating down the sides of the barrel, and it works out pretty darn well, really. The Contiki kilns are a popular style of kilns. They come in a range of sizes. They nest, so you could transport a bunch of them. They're relatively small, so they'll fit in your truck. There are a number of manufacturers out there. You can buy them commercially. They're a little difficult to fabricate on your own. They're mostly kind of backyard scale, high to very high surface to volume ratio, so not a real high efficiency. And you still got to chop your feedstock up. This is pretty good. That's a pretty decent size. But the smaller ones, you really have to dice your fuel up very small to get them in there. Here's the workhorse of the Northwest biochar. This was designed by Kelpie Wilson, based on Japanese designs that have been in use for several centuries. And the advantage of it has a bottom to minimize soil damage. But I'll tell you how you can minimize soil damage in open bottom kilns too. It can be nested for transport, but it's a small volume, relatively high surface to volume ratio, and its weight. It's all welded. It's a brick poop house, but it's hard to move 200 pounds through the woods. So it's not modular. The big box kilns like Darren McAvoy out in Utah, they have to be machine loaded because the sides are really high. This one's kind of cool because if you don't have water, you can turtle it, turn it right over. And then rather than quenching to stop the pyrolysis, you can just snuff it that way. But those are large scale, and they require machines to load them. This wouldn't work very well in northwestern forests. Kelpie's kiln, the Ring of Fire kiln, as I say, it's a double-walled kiln, so the air comes in down below and exits out the top. It's a high efficiency kiln, a low surface to volume. It's modular, so no component weighs over 40 pounds. Size for medium to large projects. Normally you put it together in 3 panels, but I was just making this slide when I happened to read something on that Kelpie was sending into one of the listservs, saying that she has put these together into 5-panel kilns before. So it is modular. It can nest. But right now, because of the damn price of steel, she has to charge $1,295 for these. But it's a great design. And it's out there, and it's been it's beyond beta testing now. It's actually, you know, into production. Whereas my kiln is I would still say it's in beta. These are panels that are double walled. You see the slot at the top, and there's a slot at the bottom. So the same thing happens. The oxygen or air comes in the bottom and then out the top. And what happens along this edge as the air comes out these slots on the top, it creates a little turbulence dam, which discourages air from sliding down the inside and getting to the bottom. Very stackable. The panels go together with no tools, and they can form polygons or rectangles, which are nice if you're cutting tops and limbs. So 8 of these panels will also turn into a 4 by 12 foot rectangle. So that worked great for fir boughs. So you minimize the amount of slicing and dicing you do out in the field with a rectangular structure. But if you have something like manzanita or hardwoods or something that are not linear, you can make them into a polygon. If you got a stump in the way, you can push, doesn't have to be a regular polygon. It can be whatever shape you want it to be in the field. And also you notice it can stair step a little bit. So as these things slide past each other, you can step them up and down the hill a little bit. So they work really well in rough terrain. So how do you operate these things? Okay, so let's go through safety feedstock, loading, firing, feeding, and quenching. Safety first. This is what I do. This is these are welding gloves. So if you need to really get in there and grab something, they work great. Face shield, I made them at the very first day I was out with a larger kiln. I cooked the surface of the coating on my glasses and ruined a $250 pair of glasses. So I would highly recommend, and this is like 35 bucks, or, you can spend 250 bucks on the firefighters, Lexan kind of, heavy duty, or you can spend 35 bucks on Amazon and get 2 or 3 of them. And if you melt one, you can replace it. And then the fire swatter. You always get little bits of stuff falling out of the kiln and it starts creeping away. You get that swatter out, whap it a couple of times, you're done. McLeod will help you kind of clean your area off to get your kiln set up. Shovel, of course, just because you always want a shovel handy while if you got fire going. And then the Pulaski especially for setting up the kiln and cutting little slots to fit it in. No synthetic clothing. If an ember lands on your nice nylon gloves, it's going to be napalm. It's going to burn and blister your hand. So leather gloves for handling the wood, welding gloves if you're really going to be, messing with the kiln, and then no synthetic clothes. So here's the kind of stands we had when we first started. Here's what we ended up with. So I mentioned before, thinning from below. So hazardous fuels, you thin from below, you're taking all that small stuff out, you're taking limbs, even on your merchantable trees, you're limbing them, you're bucking off the tops. And so you have to do something with that fuel. You can't leave it on the ground, or you're just asking for a disaster if a fire comes through that area. So as far as feedstock handling is concerned, most of you all are handy with a chainsaw, you know how to work in the woods, but this is kind of what it looks like out there. And the hard part about it is when these trees all go down on top of each other and stuff, you're doing a lot of pulling stuff out from underneath. So to the extent that you can get your faller, or if you're a faller, if you can fall trees not on top of each other, that helps you with the fuel handling. And another thing that we discovered at Yew Creek is that you can char green fuel. The conventional wisdom is that fuel has to be dry, that you have to leave it out all summer and risk all that fuel out on the ground until you char. What we did at Yew Creek was we discovered that it can be charred green. As long as you get a good flame cap going in the beginning, you can char it green. It doesn't produce more smoke. It doesn't seem to produce more smoke, and the smoke that it produces, a lot of that is water vapor too. And so we did some experiments with that. We measured the amount of moisture in the fuel. We loaded it onto my poor old flatbed and used a truck scale to measure it, subtracted the water, and it turns out that 30 to 41% of the feedstock carbon wound up in the biochar afterwards. So our preliminary results are really good. We think we can get it. We think we can do better. We think we can do closer to 50% on this, but we need a grant to be able to do a rigorous replicatable study on this. So diameter matters. Okay, so you can see we had this kind of loaded up with some fairly big stuff, and we wound up with some chunks of char left over afterwards, which is not a bad thing on the forest floor. These things have a biological role to play on the forest floor. But generally, we follow the 4-inch rule. If it's greater than 4 inches, it's an ecosystem resource, and it should stay out on the ground, for habitat for amphibians. It will store that carbon for a couple of decades anyway, 3, 4, 5 decades. And so it won't release it as quickly as the fine fuels. So you want to make sure that you go 4 inches and below. And those charred logs may be useful for hugelkultur. I coined the term chargal culture. That may or may not stick. But anyway, that's not, if you're not putting this stuff into a bag and selling it, it doesn't matter what it looks like, and it's all good out on the forest floor. So loading and firing, again, largest fuel on the bottom, fine fuel on the top. You want to keep that flame cap going consistently. If you have an open bottom kiln and you don't care if you have some unburned logs left over, put the biggest stuff on the very bottom, and that will protect the soil. So as that wood is smoldering there, it's not allowing the heat to go deeply into the soil. And we have ferns coming up in our char piles the next year. If you're going to use green fuel, this was a kiln that was lit right around the edge. Okay, so my buddy walked around with a torch and it burned into the center, and look at that cloud of thick smoke coming out here. You want to light it from the top and let it burn down with plenty of oxygen to establish that flame cap, and then it burns really clean. And then quenching. Once you get a kiln looking like this and it's all covered with white ash and the big wood is like a little alligator stuff, you're ready to quench. And so if you do have a kiln that you can break the sides down to, that helps, because you can rake that out as you quench it. So you can see here, we've pulled the front off this kiln and we're raking that char out. So the rule of thumb is about an hour before you need to quench. If it's full, great. So stop feeding and an hour later, you're ready to quench. If it's getting ready to be, if you quitting time is at 5 o'clock, stop feeding at 3, give it an hour till 4, and then you can quench from there. So that char, though, remember, it has to be charged before you can use it directly. Now, if you're just going to throw it out on the forest, that's great, because it will slowly charge as it absorbs water and minerals from the soil. But if you're going to put it straight into your garden, you can lock up those nutrients because they're all going to head for that biochar and stick to it. So you want to charge it first with, by composting, urine manure, commercial fertilizer if you're into that, 1616. But just plain old exposure on the forest soil will get it there. Okay, so that's our technology part, and I know I'm running a little long here, but this is the Natural Resources Conservation Service Conservation Stewardship Program Conservation Enhancement Activity E384A. Okay, biochar production from woody residue. Our experience with the Natural Resources Conservation Service, NRCS folks, and with their technical assistance from the Oregon Department of Forestry was great. We did a lot of education with them. They all got it. It went really well. I have a client that I did some consulting with who had a terrible experience. And so I'm going to go through the criteria and I'm going to point out the pitfalls where you're going to want to pay attention to this if you want to use this program. So here are the criteria. Additional criteria is required by NRCS. Make sure that whatever additional criteria, make sure that you have a signed copy of that. And obviously you're going to do sites where woody debris presents a fire risk and does not have commercial use. It says you should, separate by size classes. Well, of course, you're going to separate this by size class because you're only going to put stuff that's less than 4 inches into your kiln. In kilns designed for this purpose, people have been wanting to just dig a hole in the ground, throw all their wood in, light a fire on the top and bury it. Well, the NRCS isn't going to go for that because they can't monitor that. Kiln operators should be properly trained. That's you, okay? And then a plan for quenching biochar. Incorporate biochar into the forest floor. No, don't do that, because every time you open up the forest floor, what do? You bleed off carbon dioxide, you mess up a bunch of fancy little mycorrhizal stuff going on in there. Just put it on the surface and the critters will move it in, and the duff that falls on it every year will move it into the soil on a schedule more like what would happen in a natural fire. So spread it onto the forest floor. We just fling it as far as we can from where we made it. Okay. Minimize impacts on residual plant communities. You're always going to be looking to do that. And then timing of biochar coincides with period of low fire risk. And usually you're going to have to get, your local Oregon Department of Forestry, or your, we have the Douglas Fire Protective Association here, whatever your CAL FIRE, you're going to need to check in with them, even though this is much safer than an open burn. So, you don't want to present, a risk of unacceptable fire. Adequate woody material will be left on the ground. If you leave everything over 4 inches, that covers that. You can't comply with this because nobody's ever measured the amount of PM10, 25, NOx's and VOCs that come off of a kiln. It's not been measured. I understand Kelpie's doing some work. I've written 2 different grants that I haven't gotten to be able to do that work. And so sooner or later, we need to establish that. And that, of course, burning permits may be required. They'll almost certainly be required. My last warning to you, get it in writing. Make sure that everything that you talk about, any change to the plan, any, this guy had a terrible, he followed the NRCS guidelines, which say everything below 4 inches. When the NRCS guy came out, the inspector said, no, you're supposed to char everything below 6 inches. But there's nothing in writing, to say that. And so fortunately, he's going to get paid for that, but they were not going to pay him for that. So be careful, get it in writing, make sure that you have a discussion, everything gets initialed, just pay attention to dot those I's and cross those T's, and you'll have a great experience. Most NRCS staff are new to biochar, don't know how to advise or specify. Technical assistance, usually from ODF or CAL FIRE or something like that. Usually with an agency with limited or no experience in biochar too. So we need more trained contractors and consultants out there, you folks, because, we can't get crews to come out and do work for all the folks that want to do this. So there is a real need for trained people, both consultants and folks out doing the work in the woods. And so with that, thank you for your attention, and I'd be happy to answer questions, beyond 9 o'clock if you guys want to stay on with me, and if our moderators will allow it.
Wow, Ken, that was really great. Some very intense science there at the beginning, don't you all think? And so, we were planning at this point to run through any questions that were in the chat. I don't think there are a whole lot, and I bet most of them got answered already, but we're going to give it a try anyhow. And I didn't introduce Karen Taylor at the beginning, but she's my partner here at Siskiyou Permaculture, waving her hand if you're seeing the pictures. And she's been watching the chat and is going to let us know if there's any interesting things there. Ken, you might want to turn off your screen share.
Oh, okay.
I can see your face while you're talking to us now. That might be nice.
There we go.
So, wow, Karen, what have you got for us? You're muted.
Oh, doesn't look like
Karen, we can't hear you. Can't hear you. Just give it a moment here. This is Zoom. I'd be a little patient with the technology. You don't look like you're muted here. Maybe it's your microphone.
And while we're waiting for Karen, one other thing I could mention is I just mentioned the NRCS opportunity, because that's out there. We were the first the first outfit in Oregon to do, we did 32 acres of restoration and 12 acres of that was char. And so we kind of beta tested it for the NRCS in our area. But we've also got a contract where 1 acre into a 5 acre contract with U.S. Fish and Wildlife Service. So hopefully there'll be other options for federal funding for these projects going forward.
You
All
know,
right,
give that
can you
another
hear me
try.
now?
Yes.
Yeah.
Oh, good. All right, it was my microphone. All right, so I went back through the chat, and we may have to have these clarified because Marco asked, just said pH issues with biochar ? So I don't know.
Mm-hmm. Yeah.
Because you did cover pH, but he said that he didn't answer his question. So
Okay. So if Marco is still on.
I'm asking him to unmute so he can talk to us.
Oh, okay. Okay.
Yeah, my questions were pH depending on different feedstocks in particular.
Yes.
And then I had also another question on kiln design, because you and I have been in contact about bringing a kiln out to Colorado. And I've seen kilns where you actually have the biochar sort of in a closed vessel with holes on it, just allow the gases to come out.
Yeah.
I was wondering if you've experimented with like a closed sort of vessel inside the bigger perimeter vessel.
Yeah, good question. The kinds of the T-LUDs, the top load updraft types of biochar kilns are typically what you see that are enclosed with like a chimney on them.
Yep.
And so I was going to make that point earlier on when I was starting to show 55-gallon drums and stuff. I was saying because what I've been talking about are strictly the flame cap technology.
Yep.
The problem with T-LUDs is that the throughput issue. They're pretty much a batch process. You load them up, you fire them, and then whatever you got in there is going to turn into char at some point. And so the reason that we use flame cap kilns instead is because we can do a lot more volume in a shorter period of time. Because with a T-LUD, you're kind of stuck with that until it's done, until it cools, until and then you can't load it again until right. Whereas with these the flame cap kilns, it's a continuous loading process. So once you get that flame cap going, you continue to load afterwards, and that helps you maintain an even flame cap. And also you can, once you kind of get good at it, you can start to see if you've got corners in your kiln or the edges.
Yeah.
As the char starts to build up in the middle, you have the possibility of oxygen sliding down the side. So you get good at sort of spotting those and then throwing fuel into that, throwing a load of fuel into this corner. And so you're always thinking about oxygen, blocking that oxygen down in there. And so some of those other designs that you've seen with those enclosed containers are kind of are batch processors. And I mean, I suppose technically a flame cap kiln is kind of a batch processor too, but you're continuously loading it until that char fills up, and that's when you stop and quench. Or if you're 2 hours before quitting time and you're up against that kind of time constraint there. So that's a good question there. And then on the pH issue, as far as feedstock is concerned, pretty much what's happening to any of the nutrients in there, unfortunately, if you're using like high nitrogen, high sulfur material to heat, almost all of that is turning into NOx and SOx bad gases that are going up, into the atmosphere. And so you're going to lose those anyway. And so the pH of the char is going to be there's going to be very little effect on the ultimate pH of the char from the feedstock, because it's really the cellulose and the lignin that's turning into the char.
Biochar, yep. that makes
Everything else is volatilizing, and so you really don't want you don't really want much you want a minimal amount of nitrogen and other and sulfur, especially the two gases that are going to turn into your worst greenhouse offenders there.
In the woodland scenarios that you're showing where you're moving the kiln around the forest, where are you getting the water from to quench them?
Yeah, we're pretty much we've got a it's not a dedicated water truck, but we've got a 2.5 ton dump bed, and we have two 500-gallon tanks on it, and then a small Honda pump. And so we've got 200 feet of hose. So we're limited by the length of the hose. So it's 200 feet from wherever we can get that truck.
Got it.
Yeah. So working deep in, way back in the backcountry where there's a lot of stranded carbon because you can't, because there's no roads in there, that is a limitation. Water is a distinct limitation. Now, I've also got a small, what do they call it? A tracked carrier, a little walk behind tracked vehicle. And I can carry 55 gallons on that in my little 1-inch water pump on that. And so we could get back deeper into the backcountry with that. But you can't run as big a kiln with that, because then quenching all of that char is gonna, you just won't have the water to do it. Now, being able to break down the walls of the kiln as opposed to the fixed wall kilns, that really helps a lot, because once you open up those panels and pull those panels out and get them out of the way, you can rake the char out and really expose the hot spots. And what you really, it's kind of interesting, because there's two ways two things that are happening to quench that. You're cooling it down below the flash point of the fuel, right? As soon as that char, as soon as you start raking it out and it hits the air, flames, you see combustion, right? And so the more you can rake that out and see those hot spots, the more you can hit them specifically with a stream of water and cool that stuff down. And then the other thing too is that what we've discovered is that initially, on the nozzle on your hose, you can change the amount and breaking that spray up into finer droplets. As that evaporates, the heat of vaporization sucks a lot of the heat out. So rather than the water running through the char to cool it, the evaporation of the water pulls the heat out of the char. So that initial spraying, and the other thing you want to do is you want to avoid hitting the sides of the kiln in your initial spraying, because that tends to decrease the life of the kiln, because it'll warp, that shock to the metal will warp it. So you want to aim your initial spray into the center and make it a spray if you can. And then as you rake it out, you can then focus your spray a little bit more to hit those hot spots and put them out.
I have a lot more questions, but I don't want to monopolize the.
Yeah, and we can certainly go offline with this too, because we'll be, working with that kiln.
Great.
Great, thank you. Great questions. So we've got a couple of questions that have to do with soil greenhouse gas emissions.
Mm-hmm.
One of them, I think, was related to the tilling of the soil, and is asking if harrowing in seed, does harrowing in seed cause the same kind of problems as tilling? I mean, you're scraping the surface and disturbing the surface. And then the second question was, how does biochar affect soil greenhouse gas emissions?
Good question, because what can initially happen in soils that are already fairly carbon rich, you can get what's called a priming effect. When you add that biochar, you increase microbial activity, and you'll actually produce CO2 for a short time. But then as that new microbial ecosystem knits itself together, it will then hold on to more of that carbon. So you'll initially be carbon positive in some cases when you add biochar to already fertile soil, but that will be compensated in 3 to 5 years as that new microbial ecosystem becomes more and more efficient, better networks among them. Yeah, so that's a good question, because you can get this priming effect, but in the poorer the soil, the less of a problem that's going to be. Now, again, the reason that so much of even sort of big ag and stuff is going toward no-till farming now is because when you expose the carbon in the soil to oxygen, even in a well aerated soil, obviously the partial pressures of oxygen are going to be much less below the surface of the soil. And so the microbes are going to be duking it out for the oxygen that's available, right? But when you open that up and suddenly all these microbes are exposed to all this oxygen, they just have a party with all of the organic material and will metabolize that. And just like, when we metabolize, we exhale CO2, microbes do the same thing. But the flip side of that story, and I alluded to this a little bit, is that too little oxygen in the soil is going to flip the balance toward the anaerobic organisms, which are going to tend to be your denitrifying bacteria, which are going to dump organic, already fixed nitrogen. They're going to turn it into nitrogen gas, and you're going to lose it. And also the microbes that are antagonistic to plant growth are going to thrive, the root rot fungi and things like that. So you want your soil to have good structure. You want oxygen to be able to percolate in. But if you open it up and dump a whole lot of oxygen in there, a lot of your soil organic carbon is going to go up into the atmosphere. So that's why just spreading it onto the surface, is going to be your best bet. Because every year there's leaf fall, there's needle fall, there's twigs. It's going to get buried. The earthworms and soil arthropods are going to be moving the small particles in. The bigger particles are going to move more slowly. The big chunks on the surface are going to stay there, and we don't even know what goes on in those burnt brands that are sitting on the surface. We know that carbon, that biochar rind around the outside keeps them from decomposing, and so that carbon, even though it's not pyrolyzed inside of that charred log, is going to last a lot longer before it goes into the atmosphere. So all of those things are going on. You want to basically put that char back out on the ground in a way that would be more like what would happen under normal, hopefully low intensity fire situations.
Great. Next question. How do you scale up to large scale forest restoration, like 1,000 acres and more?
Yeah. There's scaling up and there's scaling out. When you build a server farm, you don't build bigger computers, right? You just string more of them together. And so if you looked at some of those projects in Utah that I showed you, Darren McAvoy's work and stuff with the big box kilns, that's scaling up, right? We're making big kilns. We're using big machines to put a lot of wood into a kiln. But in our more dense forest situations here in the Northwest, we need to scale out. So we need lots of small kilns on the ground. And so for a 1,000-acre project, you're just going to need a lot of crews out there with human-sized kilns. And again, this is very much of a human muscle driven process. And on the one hand, you know, you'd say, oh, well, geez, you know, we can't scale it up. We can't get big machines in there to do this. But on the other hand, we've got a workforce here that's already trained, that already knows how to do all this stuff, that, you know, is underemployed, you know, in many cases, that wouldn't take very much training to be able to put them out in the field. Forest contractors now that do pile and burn contracts, which is what we're competing with, by the way. So how do you get rid of this slash? Mostly you pile it up, you wait, you throw a piece of plastic on it, you know, you wait till you wait all summer, then you throw a match on it and walk away. And you have like maybe 2 to 5% char left over from that, a big dead patch of ground because it burns really hot, and all that CO2. And so what we have to be able to compete with is we have to be able to compete with those projects. We do everything they do, and then we have to sit and tend a kiln. So there's this much extra labor, there's this much extra work, there's this much extra cost in making biochar. The only way we're going to close that gap is if we're able to monetize the value of the char that we make, of the carbon that we capture, right? Because if you're making a product and you're putting that char in a bag and you're processing it, you're packaging it, you're transporting it, you're selling it, right? All those steps, yeah, well then great, you get $1 in your hand at the end of that process. But when you're throwing it out on the ground as an ecosystem service, as a service to society, you get nothing except what the NRCS will pay you. And sooner or later, we've got to stand on our own 2 feet, right? We can't expect the government to pay us to char everything, especially because we've got a ton of fuels that we need to deal with. I mean, the fires last summer here in Oregon and certainly in California happening as we speak, and all over the country, no matter where you're from, you've experienced big fires. Well, unless you're from Kentucky or something. But you know, so there's a ton of fuel that we have to deal with in the WUI, in the wildland urban interface, right? We got to get in and protect people's homes. And what's the best way to do that? Well, you can cut that stuff and chip, like the Firewise crews. They get the big chipper in and they make all these chips and they throw it out there. And what's that going to last 3 or 4 years? And it's all going to turn into CO2. It's just safer than burning it, right? Otherwise, there's no difference in 3 to 5 years. There's no difference in what's happening to the atmosphere by either burning or chipping. And so if we can get Firewise crews to be able to do the charring, we can be in close into neighborhoods, right? Because it's very safe. These things are in metal boxes and they don't produce a lot of sparks. I mean, I showed you a bunch of pictures and you didn't see a lot of sparks coming out of there. And we never have to worry about swatting, you know, spots out away from our kiln. The only thing we swat is like within a couple of feet of our kiln when the stuff falls, and we get pretty cavalier about it. We'll let it, it'll be creepy. Yeah, it's 4 or 5 feet away from the kiln. Maybe we better swat that. So it's very safe. And but I think that until we can measure, and again, I alluded to this earlier, I've been turned down on a couple of grants. One was during the last administration. And so that was, I wasn't going to get any money for that from them. But what we've got to be able to do is we've got to be able to measure carbon in, carbon out, and avoided emissions, right? So we've got to measure the plume, and we've got to do what we did. You know, you saw the big truck all loaded up and the scale underneath the truck. We've got to do that to measure how much carbon we're actually getting in biochar, and then we've got to look at avoided emissions compared to the alternate fate of that fuel, so we can do what's called a life cycle assessment and say, how much carbon are we sequestering? How much carbon are we losing in the process? And then we can go to the carbon offset markets and say, we've sequestered this amount of carbon. It's better than carbon offsets now are based on standing forest, right? Standing forests can burn down, they can blow down, they can be illegally logged. Once biochar is in the ground, nobody's going to come along with tweezers and take it out. And not only that, but your oldest forests are going to last hundreds of years, and biochar is going to last over 1,000. And so that's also got to go into the equation. And I've been working with a natural resources economist named Ernie Nemi with natural resources economics to build, once we can get him the data, he can build us the algorithm that we can then take to the carbon markets. But until we can do replicatable, publishable studies, a replicatable, publishable study to measure carbon in, carbon out, and avoided emissions, we don't have access to those markets. And so we're going to be dependent upon, it's going to be a boutique forestry project, or it's somebody who really cares about their ground, who's willing to pay the extra money, or the feds are going to pay for it. But sooner or later, we've got to make biochar break even with hand pile and burn contracts, or we won't be able to scale up. We won't be able to do 1,000 acres. We can do 1,000 acres now with 10 crews out there in a whole season, so we can scale out. But until we can get the credit for the carbon that we sequester, we're dependent on the NRCS and U.S. Fish and Wildlife and whoever else is going to be our benefactor.
Ken, I'm gonna just let's just pause and take a breath, because it is 8:59. And we did say we were going to end at 9, and I hear that you're willing to stay a little longer, and I'm willing to stay a little longer. But just sort of like take a pause here, and I'm going to mute because my phone's ringing and I don't want you all to hear it. But so that for those who want to stay, we can keep going, and let's call on Sean to ask his next question.
Yeah, my question in the chat was kind of phrased not in a good way, or is not very, in a way that's not very interesting. And I wanted to just kind of split it into 2 questions. And my first question is like, what are your ideas for like mass activation of charcoal to like economize the output for forestry operations, to try to bring in a way to make a little bit of money, while you're doing restorative forestry, not chopping down all the trees? And then my other question was, do you have, other than just like dispersing it on the forest floor, unless that's what you recommend, like, are there any other techniques for kind of getting the char into the ground in the understory of a forestry out?
Okay, so the second part of the question is, is there a way to get it into the ground? And unless you're going to charge it first, again, I would recommend to not do that, because if you just put raw char into the ground, all the nutrients around that char are going to be adsorbed by that char, and you can get nutrient lockup that goes on there. And so for a short period of time, you're going to decrease the amount of nutrients that are available to plants. So having it out on the surface not only allows it to work its way into the soil, on a natural schedule, but it's also going to give it time to charge with just the, whatever, minerals that wash down with rainwater or that wash over the surface and that sort of thing. So once it becomes saturated, it's now going to become a magnet for those ions that are going to be nutrients for plants later on down the line, or nutrients for microbes that are helping the plants grow. So the slower it goes into the soil, the better in those terms. Now, another thing that we really need to do, and this is something we need to set up a long-term productivity study where we, take a couple of hundred fairly uniform, say, Doug firs, and have a control group, and have, and drip line this tree with X amount of char, and this, the equivalent of X amount of kilograms per hectare, right? And then follow those trees for the next 50 years. And so I was saying to Melanie the other day, the best time to start a long-term productivity study is 50 years ago and second best time is now. And so if we want to have those data, in the future, because not only should we be getting credit for the amount of carbon we sequester in the ground, we should be getting credit for the increase in site productivity and the increase in photosynthetic capture of carbon and its incorporation into biomass. And I forgot the first part of your question. What was the first part?
Sorry, I had to wait to get unmuted. The first question was, what are the best methods for like doing mass, inoculation of microbiota, or like, just activating the charcoal so that you can, if you were to try to sell it, if this were to be expanded, to multiple different forestry operations, how would you kind of turn that into an economy?
Right. And so if you wanted to use your forest waste to turn into biochar that you were going to sell by the yard or by the ton or something like that, which is totally, nothing at all wrong with that. You would load your kilns a little differently. So in order to, and if you could set them up, if you could bring the fuel to the kiln and set your kiln up on a gravel area or a place you didn't have to worry about damaging the soil, that would be ideal. And then what you would do is that rather than putting your biggest fuel on the very bottom, you put some smaller fuel, some say 2-inch fuel for your first foot or so, and then put your biggest fuel in the center of the kiln, and then your flame cap on top of that. And so what's going to happen there is that the less heat will get to the bottom of the kiln, but your fuel is smaller. More heat gets to the middle of the kiln where your fuel is bigger. So you can tune the way you load your kiln. You can influence the quality of the char that comes out. So if you're concerned about, if you're dragging your kilns through the woods and just setting up at a spot and you don't want to damage the soil, but you don't care that you've got some chunks of unburned log, put your biggest stuff on the bottom. But if you want to tune it so that you get more char to process or use somewhere else in your operation. And by the way, I wanted to stick to using it in forestry, but certainly people use it in their bedding. I mean, it absorbs a lot of the it reduces the amount of ammonia that gets produced in bedding of animals, and and there's all kinds of other uses for it that I'm sure permaculture folks know all about, and lots of other people know all about, and I could talk for hours on. But as far as forestry is concerned, the second part of that is that in order to be able to compete with the fixed plant $17 million biomass one cogen plants that are the source of commercial biochar right now. So they have big boilers. They're taking wood waste from anybody. They get it for free because people are just getting rid of the stuff. I mean, it's a great business model. They burn it in their to run their boilers, to run steam, to create electricity. And then they sift the char out and they sell it for $150 a ton. And I don't think I could pay my crew. Sorry, not 150 a ton, sorry, 150 a yard, right? So, but still, when you think about, wood chips, you can get, for $35 a yard, and, all of your soil amendments are, somewhere in that neighborhood. And so the problem is economics, because you're up against major producers. So in order to have a biochar business, you really are talking about scale from the standpoint of scaling up into big equipment, big fixed plant kilns where you're trucking the fuel to the kiln. And that's right now, that's really the only way I can see to make a biochar business work as a business. Really, what we're mostly, talking about here is how to incorporate biochar into your forest stewardship so that you improve your ground, you improve site productivity and that sort of thing. And then, as I said before, I think the only way we're going to close that gap is by being able to sell those credits on the offset markets, or eventually, I guess California's got a cap and trade market, but it's only for big industry right now, but it might work its way down to biochar. Oregon is struggling to pass one. If the Republicans would ever stay in session, we could pass one. But carbon offset markets are well established. And so, different companies, different outfits are paying different amounts per ton of CO2 equivalents. And your biochar is worth about every ton of biochar is worth about 3.85, I think it is, tons of CO2. And so if you're only getting $40 a ton for CO2 equivalents, it's still tough. But I think as the situation becomes more critical, as we get more crazy fires, as we get more hurricanes, as we get more floods, I think the value of what we do as carbon sequesters is going to become more valuable.
Great. I have 3 more questions. They're all kiln related.
Okay.
The first one is, how close to the rim of the kiln can the char build up before losing the flame cap and the proper S to B ratio?
Yeah. The S to V ratio doesn't change. Surface to volume doesn't change because you still got that volume of, even though you've made all that char on the bottom, it's still that volume in there. But with the double walled kilns, or at least with mine that has the slot facing in, as the air comes up from the bottom and in, it creates a little area of turbulence along the side of the kiln to keep that oxygen from sneaking down the side. And so you can't fill it right up to the top because you need that oxygen to come in across to keep your flame cap oxygenated. So you saw that I did show that one shot of I had that 6-sided configuration where that char was all manzanita. Melanie was there in Northern California. And so you can go pretty high, but again, a lot of times we get caught in a situation, we try and we're trying to get that last burn in and we realize, we got to get the crew out of here at 5. So we got to quit loading when the thing's only half full. It really doesn't matter. The char underneath there is going to be just as good as it is if it were all the way full. So there's you can go right up to the rim, unless you have that situation like I have where you got to get a little oxygen in on the side there. Was there more to that question, or was that?
No, I've got 2 more kiln related questions though. One was, are there any concerns about roots under the kiln catching fire and burning laterally underground? That
is something that you want to pay attention to, but and of course that's a potential risk of an open bottom kiln. But when you're quenching, water's running down into the soil, and so we've never ever had that happen. And I think it's because when we quench, the excess water that doesn't vaporize winds up, especially toward the end when everything is cooling down and you're hitting hot spots, that water's going down into the soil. And that's a great question. I mean, it's good to think about all that stuff, but we've never had a problem with that. And I think, again, it's because of the quench water.
And I think this is the last question. And it's a really good one. So have you experimented with, or would it be effective to use soil capping to quench the kiln, especially if you're beyond the range of water access?
Yes, and that I've heard Kelpie has a story about that, about using soil. I think maybe with when she was out in Utah with Darren McMichaels with the big box kilns, I think they just had a front end loader and just dump soil on top of the stuff. That can work, but you have to have soil. I mean, you have to have a load of soil that you don't mind tearing up from someplace, right? And so if you're going to use soil, you're going to have to get it from somewhere. And if you're digging up soil from nearby to quench your kiln, you're kind of going to defeat part of the purpose there. I did show you that one kiln that was made out of that huge, I think it was, as I recall, that was part of a tanker car that had like the top maybe 40% cut off. So it rounded up a little bit to the top and you could roll that right over. Now you're going to get some scorch, on the ground when you do that. And we tried a number of different times early on. My original kilns were made out of old flat plate solar collector boxes that had failed, these steel panel boxes that we just sheet metal screwed together. They were like 6 by 13 feet. And we tried all kinds of, I built these snuffers to go on the top to try to so we just put the lid on the thing when we go home at night and come back in the morning and it would be char. It was a bunch of big white spots, because we just couldn't seal it. And so that the trick, if you're going to snuff, there's two problems with snuffing. Number one is sealing. Now that's an engineering problem and you can solve it. The second is that that kiln would have taken 2 days to cool down and that would have been out of commission for 2 days. So if you need to have your kilns in rotation, you either have to have a bunch of kilns that you can wait for them to cool down for a couple of days, or you quench with water, or you just work slowly and just do a little at a time. So snuffing is something that we really worked on early on because of the water issue. Because I know Marco asked that question earlier. Water is a limiting factor here for sure. So how can you do this without? Yeah, you can dump if you have a front end loader and you happen to have a bunch of soil sitting there, or you're planning if you're planning on mixing that char into soil and making it into some sort of a soil product and add some compost later or something like that, that would work for sure. But the circumstances would have to be just right for you to do that, because you just don't want to dig up soil from your environment and dump it on your kiln.
Found one more question.
Okay.
Is there a cheap or easy or both method for measuring plume emissions?
Nope. Unfortunately, there's not. I'm lucky that just an hour up the road from me is a guy named Ryan Thompson, who is an emissions engineer, and he's designed all of his own gear. It's really slick. So I'm hoping to be able to work with him. But now there is as far as measuring the amount of what you've got in your char, there's a lab. It's called Control Laboratories, and they're in Watsonville, California, and they'll do the char analysis for you. So they'll tell you how much ash you have, how much carbon, hydrogen, oxygen. I think they got nitrogen in there too. And porosity, moisture. And I think that's it. And then another measure of porosity that they use, a butane test that they do. And that's $75 a pop on that. And so that was going to be a large chunk of what we were going to ask the feds to pay for in that grant that we wrote because what we discovered was that when we did the analysis that I showed you where we captured 31 to 40% of the char, the carbon in the feedstock in the char, samples from the same kiln varied, 10% from each other. So you've got to subsample each kiln. So you have a representative sample within the kiln, and then you got to run, we think, 5 replicates of each kiln so that we have statistically significant data to be able to then publish. You wouldn't be able to publish that little study that we did. That was 2 kilns. That was three green tons of wood that we ran through 2 runs of a kiln. And the difference between the 2 kilns was 30% in one and 41% in the other. So that shows you there's a pretty big difference between the two. Now, one kiln, we put it together that day, and then we ran it for the afternoon. So we only ran 1 ton through that one, and that had the highest return of carbon. The second one was already built, so we ran it the second day all day long. We ran 2 tons through that, and that gave us a lower return. But I'm still not 100% sure that my within kiln sampling was dense enough to really give me an average for each kiln. So we plan to do a random sampling system of 5 different measurements from each kiln. And then the other thing I wanted to do was measure green versus dry, because there is the potential that charring green wood can produce more methane. And methane, as most of you know, is a more powerful greenhouse gas than CO2. And so the value of charring green, to say, well, why don't you just let it dry and char it dry? And the answer is efficiency. If you can go straight from the stump to the kiln, you handle that piece of wood 2 less times. And especially if you're piling it or windrowing it, because taking apart piles once you've made them is twice as hard as making the pile in the first place. So there's a huge amount of labor that goes into setting that stuff up to dry. Now, if you can get away with just leaving it out on the ground, and just roll the dice that you're not going to get a lightning strike, yeah, okay, you could do that. But we just found that following the cutters, right behind the fallers, and charring green was the most efficient way to handle the wood. So we're trying, everything we can. Every time you could, the fewest times you can touch a piece of wood, the more efficient you're going to be. And so we're always looking for that other little bit, and that other little bit, and that other little bit of efficiency out there that we can make this more and more and more economically viable while we're out there. And we found that charring straight off the stump saves, a significant amount of labor.
Wow, great. Thank you, everybody, for joining us tonight. And thank you, Ken. This was incredibly informative. And thank you so much for sharing your expertise and knowledge. And we have a whole bunch of thank yous from people who have already left the webinar.
Yeah, and I should say, I'm glad to, any follow-up questions you have, in the middle of the night, you think, oh, geez, I was going to ask this and I forgot. Go ahead and shoot me an email, and you can get I had it on that last slide, but you can get the contact from Melanie. It's pretty simple. It's ken.carloni@gmail.com. So please, if you have any questions, any ideas or things that you forgot to ask, or burning questions that pop into your mind, please ask, and I'll be happy to answer them to the best of my ability.
Yeah, when can we come visit you at Yew Creek Alliance?
Yeah, well, I really hope, I was hoping that maybe as far as the rest of your project here, especially, if you're looking for a piece of ground to work on for this, this grant. I've already offered Melanie that, we're Southern Douglas County, so we're a little ways up from the Applegate there, where I think most of you folks are maybe. We'd be glad to host, part of a workshop up there, or part of your project, or organize another workshop up there. We're always happy to. We're really jacked about what we've done up there, and we're happy. we're very, very glad to take people up and show people around, and whatever we've learned, we're happy to share, with anybody else.
Thank you, Ken. Thanks for your incredible generosity of your time and your expertise and your passion. We're immensely grateful. And let's call it a night.
Okay.
Thank you, everybody who's still here, for coming, and all of you who have already left. We appreciate your presence and all your great questions. Good night, everybody.
Night.